The main purpose of this lecture is to show how volumes are computed in curved spaces and curved spacetimes. Before doing that, I want to take a few minutes to sharpen our intuition for vectors. As we know, vectors are derivative operators. For example, here's a parameterized curve, parameterized by lambda. And we can, well, let's say this is the point lambda equals 0. Here's lambda equals 1, lambda equals 2, and so forth. Now we can define the derivative operator d by d lambda at any point along this curve. And expanding this in a coordinate basis, this is partial x mu with respect to lambda d by dx mu. And these coefficients of the basis vectors are the components of the vector v. So the components are just the derivatives of these functions x mu of lambda with respect to lambda. Now let's pick one of these vectors along the curve, say the vector at lambda equals 0. I want to draw that vector as an arrow. So let me do that. So this is the vector v at lambda equals 0. The question is, how long should I draw this arrow? Now previously, when I've drawn pictures like this, I've treated the length of these arrows pretty loosely. I haven't really specified or had any particular meaning behind the length that I've drawn the arrows. But let's think about this for a moment. This is space or space-time, and we have a metric, so we have a notion of distance between neighboring points. So for example, if these are neighboring points along the world line, we can compute the distances along the world line. It's a certain time or space interval. And how should the length of the arrow be correlated with distances in space or space-time? Well, the mathematician would say that the length of this arrow is not correlated to the distances in the space or space-time because the arrow actually lives in a different space. So a mathematician would say that the mathematician would refer to the space or space-time as a manifold. Space or space-time is a manifold. And the vectors live in the tangent space to a point on the manifold. The tangent space to a point. So there's a tangent space at each point in the manifold. So the mathematician would say what this picture really represents is a superposition of two pictures. One picture is a picture of the tangent space, where the vector is pictured as an arrow in the tangent space, and that's superimposed on the manifold or the space or space-time itself. And so there's really two length scales going on here. So that's the mathematical point of view, and that's the correct point of view. But I'm not really much of a mathematician, so I want to think about this a little bit more like a physicist. So let's return to our expression for the vector in a coordinate basis. And let's interpret the derivative as a small change in the coordinates x divided by a small change in the parameter value lambda. All right, so this is the derivative of x with respect to lambda in the limit as delta x and delta lambda go to 0. All right, so written this way, let's multiply through by delta lambda. We have delta lambda times v is equal to delta x mu d by dx mu. Now this is a vector on the left, and so we can call this anything we like. For example, we could call it w, or we could call it v and just absorb the delta lambda into this v if we like. All right, and this is that vector, whatever you want to call it, this is the expansion of that vector in a coordinate basis. So the components of the vector, let's just go ahead and call them w mu, are delta x mu. So this vector that I'm now calling w, I can think of as a displacement vector. All right, so it's a vector that points from some event or point with coordinates x mu to x mu plus delta x mu. And here's the vector pointing between those particular points. And we can see that we have the length, this is the correct length to draw this displacement vector, because we can compute the length of this vector. The length of a vector is just, or the squared length to be precise, is just the inner product of the vector with itself. So that's just W mu, G mu nu, W nu. But the components of the vector W are just delta x mu, the change in the x coordinate values. So that's G mu nu, delta x mu, delta x nu. And this is, of course, just, well, if I interpret these delta x's as dx's, this is just the line element. All right, so the squared length of the vector is equal to the proper distance between these 2 points. So let me turn this around. If we have 2 points, say point x mu and another point x mu plus delta x mu, and we want to construct a vector that points from x mu to x mu plus delta x mu and has length equal to the proper distance between them, the vector is just this displacement vector. Okay, so it's just the vector with components equal to delta x mu. So the vector is delta x mu d by dx mu with components delta x mu. And that's the displacement vector. Now let's turn to the question of how we compute the volume of a region of space or space-time when it's curved. And by the way, the term volume here is used generically, independent of what the dimension might be. In the case of two-dimensional spaces, I'll often refer to, instead of volume, I'll use the word area. So let's start with a simple example. Let's take two-dimensional space, flat space. How do we compute the area of two-dimensional flat space of a region? Well, the easiest way is to set up Cartesian coordinates. So we have a coordinate grid that looks like this. And for example, this coordinate cell has sides delta x and delta y. And we know the area of that coordinate cell, area, is equal to just delta x times delta y. All right, so the area is then the sum over all these little coordinate cells, delta x times delta y. And of course, we convert that to an integral over dx dy. So what do we do if the space is curved? Well, let me remind you of some things we know. Recall that if we have space-time, we can always construct Fermi normal coordinates about any geodesic. So Fermi normal coordinates are a set of coordinates that, in a neighborhood of a geodesic, so this is a geodesic, a time-like geodesic, we have a system of coordinates in which the metric looks like flat metric, flat space-time in Minkowski coordinates. So G mu nu has the form of eta mu nu, flat metric in Minkowski coordinates, plus quadratic terms. or quadratic corrections, terms that are quadratic in the spatial coordinates. So in particular, along the world line, these terms are equal to 0. Now we could carry out this same kind of analysis for space. So let's say that here's some curved space of, I don't know, 2 or 3 dimensions, or it doesn't matter how many dimensions. We can always find a geodesic through this space, and in the neighborhood of the geodesic we can find coordinates. So there's the coordinate grid in the neighborhood of this geodesic, in which the metric, let's call it in this context Gij, where ij run from 1, 2, and maybe 3 or higher. This is just equal to the metric for flat space in Cartesian coordinates plus quadratic, small quadratic terms. So this is flat Cartesian metric. Okay, so we can do this along any curve. So what about in the neighborhood of a point? If we can find coordinates that make the metric look flat and Cartesian along a curve, we can certainly do it at a point. So here's my curved space. Now pick a point, say right here. We can always find a geodesic that passes through that point, and we can construct coordinates in which the metric looks flat and Cartesian. So let me draw the coordinates in the vicinity of this point like this. All right, so in the neighborhood of this point, we have Gij, just looks like the flat metric and Cartesian coordinates plus small terms that are quadratic in the spatial coordinates, so they vanish at this point. Now, we know how to compute the area, say, of this coordinate cell. Okay, in particular, the area is just delta x times delta y, right? Because the metric is just flat Cartesian coordinates, and as we shrink the size of the cell down, these quadratic terms go to 0. So the area of this cell is just delta x delta y. Now, the difficulty we have is that we can't really use delta x times delta y to compute the area of these other coordinate cells, because as we move away from this point, these quadratic terms become larger and larger. So the lengths of the sides of these coordinate cells, the proper lengths of those sides, are no longer just equal to the coordinate lengths, delta x and delta y. Now, you could always argue that I could find the area of a coordinate cell, say in this region, in the neighborhood of this point, by doing the same construction, setting up coordinates here in which the metric is just the flat Cartesian metric plus terms that vanish at this point. That's correct, and then I could compute the area as delta x, delta y. The problem is that coordinate mesh is not the same as this coordinate mesh. So that would be a coordinate mesh that has coordinate lines that may look something like this. So I'm really computing the area, say, of this little region. So I can't actually use this simple formula for the area of the coordinate cell, except for this central one. I can't use it for these other coordinate cells away from this central point. And remember, my goal is to be able to find the area of each little coordinate cell so that I can add them up to find the area of this whole region. Okay, but what I can do is use the fact that the geometry around any of these little coordinate cells is flat. And we know this because we know it's possible to set up a coordinate system around that coordinate cell in which the metric looks like flat space with Cartesian coordinates. We just can't use those coordinates in computing the volume. Okay, so using the fact that the geometry in the neighborhood of each coordinate cell is to a high degree of approximation flat, and in the limit as the coordinate cell shrinks to 0 in size, we can treat it as completely flat. So let me draw you a picture of one of those coordinate cells. So here's some of the coordinate lines, say like this. And now what I'm drawing, I do want you to think of this as being a flat. So the geometry here on the screen or the piece of paper is a flat geometry, but the coordinates are not Cartesian. So here's a general coordinate cell, and let's label these points. Let's say this is, we'll call the coordinates x and y. So this is a generic point x comma y. This is the point x plus delta x comma y. This is the point x comma y plus delta y. And finally, this is the point x plus delta x comma y plus delta y. Remember, we're going to be taking the limit as delta x and delta y shrink to 0. And in that limit, we can take these coordinate lines to be straight lines, and this cell then is a quadrilateral. So, what is the area of a quadrilateral? Well, you can look this up for yourself if you don't already know. The area of a quadrilateral can be computed as follows. We take this vector, let's call this vector v1, and this vector, let's call this vector v2, and then the angle between the two vectors we'll call theta. The area of a quadrilateral is given by the following formula. It's 1/2 the length of v1 times the length of v2 times the sine of the angle between the two. Of course, this should be v2. Now these vectors v1 and v2 are just displacement vectors. So for a displacement vector, the components are just the changes in the coordinates. So the components of v1, well, the change in the x coordinate is just delta x, and the change in the y coordinate is delta y. And for v2, the components are, well, the change in the x coordinate is minus delta x, and the change in the y component is delta y. So those are the displacement vectors v1 and v2, and the angle between them can be computed from the dot product. So the cosine of the angle is the dot product of v1 and v2 divided by their magnitudes. In putting this together, we can find a fairly simple formula for the area. We have 1/2 magnitude of v1, magnitude of v2, times sine of theta, which is 1 minus cosine squared. So that's v1 dot v2 squared divided by the magnitude of v1 squared and the magnitude of v2 squared. So bringing these factors under the square root, we have 1/2 square root of v1 magnitude squared, which is v1 dot v1, times v2 magnitude squared, which is the dot product of v2 with itself, minus v1 dot v2 squared. All right, so we just need to compute these dot products for these vectors, v1 and v2, and I'll remind you v1 has components delta x, delta y, and v2 has components minus delta x, delta y. So let's begin this calculation by computing the dot product of v1 with v2. Right, so the dot product is always computed using the metric. So in terms of components, we have the components of v1 times the metric gij times the components of v2. And the metric, what do we know about it? Well, we know the metric represents a flat geometry. But that doesn't really give us any useful information about the metric itself because the coordinates could be arbitrary. So let's just write the metric as g11 dx squared plus 2g12 dx dy plus g22 dy squared. Right? Then this inner product is v1 dot v2 is v1 is delta x, comma, delta y. The metric is g11, g12, g12, g22, written as a matrix, and v2 is minus delta x, delta y. All right, so this simplifying, let's multiply the metric times v2, that's minus g11 times delta x plus g12 times delta y. And for the second component, we have minus g12 delta x plus g22 delta y. Then simplifying that, we have delta x times all of this. That's minus g11 delta x squared plus g12 delta x delta y. Then delta y times this term is minus g12 delta x delta y plus g22 times delta y squared. These two terms cancel to leave us with minus g11 delta x squared plus g22 times delta y squared. Now the calculation of v1 dot v1 is very similar. It's just this delta x has a plus sign instead of a minus sign if we change this v2 to a v1. And that removes these minus signs, removes these two minus signs. So these two terms don't cancel. And this term comes in with a plus sign. So v1 dot v1 is just g11 delta x squared plus, from these two terms, g12 delta x delta y plus g22 delta y squared. And that, of course, is what we expect because that's just equal to ds squared. Whenever you square a displacement vector or take its inner product with itself, it should just give the square of the distance between the 2 points that it connects. So from this point to this point, the proper distance is just given by the metric with dx and dy replaced with delta x and delta y. And for the dot product of v2 with itself, it's just this distance. And actually here the change in x is negative, what's being called here negative delta x. So that just flips the sign of this term. So v2 dot v2 is g11 delta x squared minus 2 g12 delta x delta y plus g22 times delta y squared. And again, this is equal to ds squared, the proper square of the proper distance between the 2 points connected by v2. It just looks funny with this minus sign because the change in x is actually minus delta x in this case. All right, so let's put all this together to find, this is v1 dot v2, to find the area. Recall that's 1/2 square root of v1 dot v1, v2 dot v2 minus v1 dot v2 squared. All right, so that's equal to 1/2. And let's multiply this out. Let's group together the g11 delta x squared and g22 delta y squared terms in both of these factors. So we have g11 delta x squared plus g22 delta y squared squared. And then squaring these two terms, we have, multiplying these two terms together, when we multiply these, we have minus 4 g12 squared delta x squared delta y squared. And when we multiply this term times g11 and g22 terms from here, that will cancel what we get by multiplying this term times the g11 and g22 terms from here. So this is the result of this first part of the calculation. And now we need to subtract v1 dot v2 squared. So here's v1 dot v2. So that's minus, the square of this is g11 squared delta x to the fourth minus 2 g11 g22 times delta x squared delta y squared plus g22 squared delta y squared, close brackets. All right, now we just need to simplify this a bit. This is 1/2 g11 squared delta x to the fourth plus 2g11 g22 delta x squared delta y squared plus g22 squared delta y to the fourth minus 4g12 squared delta x squared delta y squared minus g11 squared delta x to the fourth plus 2g11 g22 delta x squared delta y squared minus g22 squared delta y to the fourth. That should be a 4 here. All right, so we should have some cancellations here. These terms cancel. These terms cancel. And we have, you'll notice these two terms are the same, so we'll have 4 of those. That's 1/2, and all of this, by the way, is to the power 1/2. Okay, it's under the square root. So this is 4 g11 g22 from these two terms minus 4 g12 squared from these two terms. All of these have a common factor of delta x squared delta y squared. And all of this is under the square root. So the area here, we see, of course, these 4's, when we bring them out from under the square root, cancel the 1/2 here. And we can also bring the delta x and delta y out. And we're left with the square root of g11 g22 minus g12 squared times delta x delta y. Now this combination of metric components under the square root you should recognize immediately as the determinant of the metric, the determinant of g11, g12, g12, g22. And this, the usual practice is to denote this by just the letter G. So G is shorthand notation for determinant of the metric components. And by the way, in the past I've used G to denote the metric tensor, thought of as a 0-2 tensor, Gij dxi, and to be very careful here, I'll use the outer product symbol. The G in this context, of course, is different from this G. Usually in textbooks, people would write this G, say, as bold-faced. I'll just go ahead and use little g for the determinant of the metric, and I'll also occasionally use little g for the metric tensor itself. And I think from the context, there won't really be any confusion here. So using little g to denote the determinant of the metric, our final result for the area of a coordinate cell is square root of little g, the determinant of the metric, times delta x times delta y. And the area of any finite region can then be obtained by just integrating this over the region. Integral square root of g times dx times dy. And the analogous result holds in any number of dimensions. So in an n-dimensional space, the area or volume is equal to the integral of square root of determinant of the metric times dnx. So dnx is just shorthand for dx1 times dx2 times dx3 and so forth. All right, let me give you an example. Let's look at the volume of a sphere. So let's use spherical coordinates. So the line element is dr squared plus r squared d theta squared plus r squared sine squared theta d phi squared. Right, so the determinant of the metric, well, the metric, let's go ahead and write it. It's 1 r squared and r squared sine squared theta along the diagonals, 0 everywhere else. So the determinant of the metric is just the product of the diagonals. So that would be r to the fourth times sine squared of theta. Then the volume is integral of square root of g, that's r squared times sine theta, times dnx, so the coordinates are r theta and phi. So this is dr d theta d phi. So for example, if we want to find the area of the whole sphere, we just integrate r from 0 to, say, capital R, whatever the radius is. Theta goes from 0 to pi. Phi ranges from 0 to 2 pi. And we have r squared sine theta. So if you carry out this integral, you find the usual result, 4/3 pi capital R cubed. So here we have the general result for the volume of n-dimensional space. What about the volume of space-time? So the volume of a region of n-dimensional space-time is equal to the integral of square root of minus the determinant of the metric times dnx. So it's the same expression except for the minus sign. All right? Minus. So the determinant of the metric in a space-time is always negative. And you can see that quite simply by looking at flat, for example, just look at flat space-time in Minkowski coordinates. And we can add more dimensions here if you like. All right, if I take the determinant of the metric, it's diagonal, so it's just -1 times +1 times +1 +1 and so forth. So here the determinant of the metric is equal to -1, and the negative of that is, of course, positive, and so we can take the square root. So in fact, if you want to know the difference between space and space-time, here's one way of defining it. Space has determinant of the metric positive, whereas space-times have determinant of the metric negative. Now you might wonder whether this distinction makes any sense. After all, we can change the metric quite a bit by just changing coordinates. So, for example, is it possible to change the sign of the determinant of the metric by changing coordinates? Then by this definition, you could change a space into a space-time and vice versa just by changing coordinates. But that's not possible. Remember how the metric changes when we change coordinates. So here's the metric tensor, not the determinant. So we can expand it in some coordinates x mu with coefficients g mu nu, and we can expand it in another coordinate system x bar mu with components g bar mu nu, and then by writing x bar in terms of x and expanding out these differentials, we find that the components in the barred coordinate system are related to the components in the unbarred coordinate system by an expression like the following. We have partial x alpha with respect to x bar mu, partial x beta with respect to x bar nu, times g alpha beta. So the determinant of this, the metric tensor in the barred coordinates, so let me write that explicitly as determinant g bar. It's equal to the determinant of what's on the right-hand side here, but remember when you have a product of matrices, the determinant of the product is the product of the determinants. So this is the determinant of this factor partial x with respect to x bar, times determinant of this factor again, so we have two of those, times determinant of the metric in the unbarred coordinates. So you'll see that the determinant of the metric in the barred and unbarred coordinates are related by a factor that's always positive because it's squared. So whatever the sign of g is, the sign of g bar will be exactly the same, which is to say that we can't change the sign of the determinant of the metric by just making a coordinate transformation. So again, spaces always have g positive and space-times always have g negative. And the volume of any region of space-time is given by this integral. And of course, square root of minus g times dnx is just the volume of a single coordinate cell. So this is the volume element. Square root of minus g times dnx. Or in the case of four-dimensional space-time, d4x. Right? And this is useful in a number of contexts. It shows up, for example, when we write down action principles in curved space-times. So let's look at electromagnetism. Right? We can describe the electromagnetic field in terms of a vector potential, A, and the action, it's a functional of the vector potential. It's given by the integral of the volume element, d4x square root of minus g, times the field strength tensor wired with itself in this way. So here, F mu nu, the field strength tensor, is defined as covariant derivative mu a nu minus del nu a mu. And so by writing the field strength tensor in terms of the vector potential, two of Maxwell's equations are automatically satisfied, and the other two come from varying this action or extremizing this action with respect to A. And I'll also remind you that, so this is the definition of F with the lower indices, and F with the upper indices is obtained by raising those indices. So this is just shorthand for G mu alpha, G nu beta, F alpha beta.